What's up, guys? It's Mike97 back at you with another operating systems tutorial. In the previous tutorial, we talked about the A20 line and how to tell if it is enabled on your CPU. And if you don't know anything about what I just said, then go back to part 8. Link is in the description and watch it, and you will learn many things. And if you do know what I'm talking about, then venture on with me. So, the A20 line having such a history results in a plethora of ways that we can enable it. That was a weird way of saying it, but you get the idea. So there's 3 big ways that cover like 99.9999% of the things that you're going to encounter. And those 3 ways of enabling it is going to be with BIOS, which is going to be by far the most common. And if that doesn't work, the second way is with a keyboard controller, because back in the days of the Intel 8042 keyboard controller, they had a pin that was reserved for enabling the A20 line, which is a bit silly if you think about it now, but back then I guess it made sense. And since a lot of keyboard controllers today are kind of cousins of that, there's a possibility that a keyboard controller will be a way to enable the A20 line, so that's the second test. If that doesn't work, the last and final test is the fast A20 method, and what that is that it communicates with the chipset, which potentially will turn on the A20 line. The reason why we'd put this one last is because it's also the most unpredictable test. Sometimes it can result in a kernel reboot, so in other words, your system crashing. So that's why it's last, and if that doesn't work, then I guess you're SOL, and you probably don't have an A20 line. So without further ado, let us start. The BIOS interrupt that we use for enabling the A20 line is the interrupt 15 hex. So let me create the enable A20, and we'll create our function label. Okay, so first we're going to do BIOS, right? So what you need to put in to your AX register for this to work is 2401 hex. So your A high is 24, your A low is 01. So I'll just do that, 0x2401, and we'll call the interrupt. There we go. That's it. Now what we can do is we can use our test A20 method that we created last time, and we can compare AX to 0, and if they're equal, AX to 1, because it returns 1 in the AX register if the A20 line is enabled. And if it is enabled, so in other words, if AX and 1 are equal, then we can go to done. Yeah, let's just do that, done. And we'll create done down here. Done will read pop A, and actually, yeah, let's go ahead and just push everything to the stack. Push A, there we go. We'll pop A, move AX to 1, and return. And then down here, we'll return. Okay. So let's go ahead and test this. Keep in mind, over here, we don't have anything going on with our enable, so we'll just create, well, also, you should update your makefile. I've already done that, but you should update your makefile to include the enable A20. In any event, we'll just see what it looks like when the A20 is off, which is what it currently is thanks to that. So when the A20 is off, when we return AX, we get 0. So what's going to happen is when I uncomment this stuff, we'll call enable A20, and then we'll print out AX again, and it should be 1. So let's, and then we got to include it. Make run. Aha! Look at that. So it's 1. Alright, so the BIOS works, and it's going to work. Every single test is going to work in QEMU, which is great. That way we can make sure that what we're doing is right. In our case, we wouldn't need to go through every test. The first one would work, and really, it would work anyway because QEMU automatically does it, like most BIOSes do. But we will write the next one up. Good lord. Write the next one up, and we'll test that one independently as well. So, vim enable A20. So we'll just go ahead and comment this out. Keep done, because we'll use that. This one is the keyboard. Okay. So the keyboard is a little more complicated. When you speak to a controller through the CPU, like a keyboard controller, you access it, so you send out commands and read in data through what are called ports. And a keyboard command port is port 0x64 or 64 hex. And the data port, the keyboard data port, is 60 hex. So 64 hex and 60 hex, those are the 2 ports we need to concern ourselves with. The keyboard is a little weird though. The way the controller works is it might be busy and it might not be busy. It depends. So before we do anything, we need to create a loop so that basically waits until the controller is not busy before allowing us to send in a command. So we'll call this wait C. Okay, and likewise we need to do the same for data. So we need a loop or a little function that loops until there is data to be read if we're trying to read data from the controller. So we'll call this wait D. Alright. So we're going to introduce ourselves to a couple of new commands. The first of which is in. And what in is it takes in data from the keyboard through port 64 in our case, and stores it to a register. So AL0x64. Okay. Then the second command that we're going to learn is test. Test is a bit comparison. CMP is an arithmetic comparison. So what CMP does is it tests one register versus another by subtracting the two, and if they're 0, then they're equal. Test doesn't do that. What test is, it looks at specific bits and determines if those bits are equal to each other, or if in other words, if those bits and together yield a 1, then test returns a 1. And if they're different, it returns a 0. So basically test is an AND gate. But it deals with specific bits of an input. So for our command here, or for our wait C function, we're concerned with the second bit. So, I mean, what we could do, we could do this by masking the second bit and then using binary AND, but that would take more time and it would take more memory. So this is the easiest way to do it. So test, and we'll look at the second bit. If the second bit is 1, that means it's busy. And if it's 0, that means that it is not busy, so we can continue. So we're going to use J and Z, so jump if not 0 to wait C. So if it's not 0, then which means it's 1, which means it's busy, we go back to wait C. If it is 0, we continue and just return back. Wait D is incredibly similar. In AL0x64, so we get data from our port 64. And this time we are looking at bit 1. So if bit 1 is 0, that means that the data is ready, and if it's 1, that means it's not. So instead of doing J and Z, we're going to do JZ and wait D and return. And that's all there is to those. So now back to the regular keyboard, or back to actually programming the thing. There's a few steps that we need to go through in order for this to work. So the first of which is disabling the keyboard. So it's the second of which, and the reason we do that is because we don't want any like interruptions or interference with the keyboard and anything. And in doing that, we also disable interruptions. Or interrupts, I'm sorry. Then we need to use our wait C to basically tell the controller that we want to read from it, and then we'll read an input, or we'll read a piece of data, a byte of data from bit 2. We'll read a byte of data and then we'll do the same and output it, masking bit 2. So what that does is it's just going to send bit 2 over, which will potentially enable the A20 line. And then once we're done with that, we re-enable the keyboard, and basically that's it. So to start, let's enable the keyboard. So the command for enabling the keyboard is hex AD. So we will let's see, call wait C, let the controller know that it should be, or wait for the controller to accept a command. Move AL to 0xAD, and then out is the last new command we're going to learn. And out sends our data from whatever register, in our case AL, to whatever port, in our case port 64. So to 64 AL. And so basically what we've done is we've used this command code and we've sent it through port 64 as a command. And that disables the keyboard. Now we need to tell the keyboard that we want to read from it. So we'll call wait C again. And this command is D0. So do the same thing and send that command out, 0x64AL. So now that it knows that we want to read from it, we can actually get the data. So we'll call wait D, wait for the data to be ready, and then when it is ready, we will read that data into register AL from port 060, which is the input port, like the read port if you want to think about it that way. And then we'll push AX so we can save that for later, because we're going to end up wanting to use it to mask it and then send it back off. So to do that, to mask it and send it back off, call wait C and let the keyboard know that we want to send it data. So not command, but data. So we will use the command AL 0xD1. That lets it know that we're sending it data, and then we'll send it out 0x64 AL. And then finally, we'll write back the input data, which is currently on the stack, masked, the masked input data, which is currently on the stack, and we'll mask oh my goodness gracious, we'll mask it to write the second bit back. Okay, sorry, words are kind of hard right now. Alright, so we'll call wait C again. We'll pop AX from the stack. We'll bit mask it. So we'll mask the second bit, and then we'll send it out through port 060, which is like our data port. Okay. Now that we've done that, we're almost there on the home stretch. We just need to re-enable the keyboard and set it up for further commands. So we'll call wait C. We'll move AL to 0xAE. If you recall, it was AD up here to disable. To enable, it's AE. And then we'll send that command out through port 64. And then we'll open it back up for commands. We will reinstantiate interrupts and return. And we should probably instantiate interrupts. I keep forgetting to do that. Okay. Whoops. STI. There we go. Before we return, we can then call our test A20. Compare AX to 1. JE done. Else return. Okay. What line? 31. I wrote A1, AL. There we go. There we go. Haha. The keyboard input works, or the keyboard controller works. So remember, we commented out BIOS. Now all that's running is a keyboard controller. 0 means it doesn't wrap, or it wraps. In other words, the A20 line is disabled. 1 means it's enabled. Alright, that's wonderful. So now let's do the last one. Last method is super simple and quick. Let's see, okay, there we go. Last one is the fast A20. This one communicates with the chipset. So we're going to use port 92 to do that. And unlike the keyboard, there's no, it doesn't have to wait to be ready for something. So, you don't have to wait for it to be not busy to send it a command. It's ready. So we don't have to worry about the, wait C, wait D nonsense, which is why it's called the fast A20. Since it's down here, not exactly super fast, considering we'll have gone through 2 other checks, but regardless, so we're going to use port 92. So in AL 0x92, we'll mask bit 2, so or AL2. And lastly, we are going to send that new data back out. So out 0x92 AL, and we're done. That's it. So we'll call test A20, compare AL to 1. If it's equal, we will jump to done, else return. Oh, and I probably should have done this anyway, but let's just XOR AX right now, just to make sure, you know. And it works. So all three of those work. So we know that they are good should they ever have to be used. So I'll just go ahead and uncomment all of these. Yeah, that's basically it. It was kind of an ordeal to go through with these keyboard stuff, and all three tests seems a little bit overkill sometimes, but this is the best way to do it. The reason we do it in this order is because the BIOS is going to work like 9 times out of 10. If it doesn't work, the keyboard controller isn't like unheard of. It's possible that could happen. You can have a keyboard controller and have it work. The reason we put the fast A20 at the end is just because it's unstable. So, well, not unstable, but unpredictable, really. If it works, it works. If it doesn't work, it can be known to crash your system. So that's why it doesn't go first, because if it goes first and your system is one of the systems that it crashes on, then you'll never get it enabled and you'll never boot. So that's basically it. Hopefully I'll just you know what, I'll go back up here for all of these XOR AX and do that just to make sure that we're not getting a 1 output every time. And XOR AX. So yeah, hope I'll see you next time. Next time we're gonna determine, since we're writing a 64-bit operating system, we need to determine if the CPU is 64 bits. So next time we will come up with a way to do that. It's once again kind of a strange method, but it works all the time. So, you know, if it works, it works. And that'll be the next one. And then after that, we'll get started on setting up a global descriptor table for 64-bit system. The way we end up transitioning to 64 bits is we have to go through protected mode first, which is 32 bits. So we'll set up a 32-bit GDT, and then we'll go into protected mode. Once we do that, alter the GDT to be for a 64-bit system, switch into long mode, which is the mode for 64 bits. Once we're out of 16-bit real mode, which is what we're in now, we have no BIOS, so that's where it kind of really starts. And once you get into long mode, you're basically writing the kernel. So we're getting there. It's coming. Now that I'm done with classes for the summer, I should have some more time to work on this stuff. So hopefully you'll be getting videos out a little bit more frequently than like once a month. Anyway, appreciate you watching this. Hopefully you're learning something. It's fun to do, and I'll see you in the next video.